All right, let's talk about a huge problem that's been nagging the world of AI for a while now, and a surprisingly simple idea that might just be the fix we've been looking for.
To really get what's going on, you have to understand the scale we're talking about. A modern AI model, like Llama 2, can have 70 billion parameters. You can think of those as the tiny little knobs and dials in a giant electronic brain. And as you can probably guess, running a brain that big costs an absolute fortune in money and in pure computational horsepower.
So, here's the game plan for today. We're going to start with this billion-parameter problem. Then we'll see why a really common old-school trick just stopped working. After that, we'll get to the aha moment that changed everything, see how the new kid on the block stacks up against the competition, and finally, talk about what this means for a future of smarter, leaner AI.
Okay, so these giant models are amazing at what they do, no question. But their size, it's a classic double-edged sword. All those billions of parameters mean they're incredibly expensive to train, super expensive to actually run, and really, they're only accessible to a handful of companies that can afford these massive supercomputers. And that brings us to the core issue. If we really want AI to be for everyone, to unlock all that potential, we've got to figure out a way to shrink these things down without making them dumber. Honestly, this is one of the biggest puzzles in AI research right now.
Now, if you want to make something smaller, what's the first thing you think of? You just trim off the extra bits, right? Well, in the world of AI, that process is called pruning.
It's kind of like being a gardener for a bonsai tree. You carefully snip away the little branches that aren't really doing much, and you're left with a smaller, healthier, more efficient tree. For years, AI researchers had a really simple rule for deciding which connections to snip.
That rule was called magnitude pruning. It's dead simple. You just find the connections, the weights, that have the smallest numbers, the ones closest to zero, and you chop them out. And for older, smaller AI, this worked like a charm. But when they tried this on the new generation of large language models, it was an absolute disaster. The model's performance didn't just dip, it completely fell off a cliff. So what happened? Why did this trusty old tool suddenly break?
Well, that massive failure turned out to be a huge clue. It told researchers that they were missing a really important piece of the puzzle. The problem wasn't pruning itself, it was how they were deciding what to prune. And this led to a brilliant aha moment.
Okay, let's look at a super simple example from the paper that figured this all out. Say you've got an output, y, that comes from two inputs, x1 and x2. Each input is multiplied by its own weight, w1 and w2. The old method, magnitude pruning, only looks at the weights, so if w1 is a smaller number than w2, it gets the x. Every single time. Simple, right? But it's also dead wrong.
And this question is the key to the entire mystery. What if the input signal coming in matters too? It turns out that these big language models have something called emergent large magnitude features. All that means is that some inputs are just naturally way more powerful than others. Think of it like some signals are screaming while others are just whispering.
And that just perfectly shows the flaw in the old way of thinking. You see, even if the weight, W1, is tiny, a very small number, if its input, X1, is massive, then the total information flowing through that connection, the weight times the input, is actually the most important part of the entire calculation. Getting rid of it just because its weight was small would be a catastrophic mistake.
And that brings us to the breakthrough from a new method called Wanda. The idea is so simple, it's beautiful. Instead of just looking at the weight, you create a new importance score. You take the weight and you multiply it by the typical strength of the signal that passes through it, what they call the activation norm. This new score looks at the whole picture, not just half of it.
But wait, there's more. Wanda has another clever trick. The old method would look at a whole giant layer of connections and just chop off the bottom half. Wanda is much more careful. It looks at each individual output neuron, one by one, and removes, say, 50% of its specific inputs. It's a much more balanced surgical approach.
Okay, so this new Wanda idea sounds really smart in theory, but how does it actually do in the real world? Let's throw it in the ring and see how it stacks up against the old, simple method and the previous, much more complicated champion, a method called SparseGPT.
First off, let's just appreciate how elegant and simple this is. It's a three-step dance. Step 1, run a little data through the model to see which pathways light up the most. Step 2, calculate that new importance score for every single weight. And Step 3, for each output, you just snip the connections with the lowest scores. That's it, you're done. No complex follow-up math needed.
This little table here really tells the story. See that weight update column? Unlike sparse GPT, Wanda is one shot. It doesn't need to do a whole second round of expensive calculations, which is a huge deal. Now look at complexity. All that O notation is just a fancy way of saying how much slower things get as the AI model gets bigger. Wanda finds this perfect sweet spot. It's way more powerful than the simple method, but it avoids the absolutely crushing slowdown of sparse GPT.
And here's the proof. This chart shows a score called perplexity. All you need to know is that lower is better. The old magnitude pruning method? It's a total disaster, way up at 17. But look at Wanda. It's right there, neck and neck with the super complex sparse GPT. It gets basically the exact same fantastic result, with a way simpler approach.
But here's the knockout punch. Not only is Wanda just as good and way simpler, it is also ridiculously fast. The researchers found that it can figure out which connections to prune up to 300 times faster than its main competitor. That is not just an improvement, that's a complete game changer.
So, okay, this is a really cool technical discovery. But what does it actually mean for us in the real world? Why should we care about making AI smaller and more efficient?
Well, it enables a future of AI that's leaner and available to everyone. It means we could one day have powerful AI running right on our phones, on our laptops, without needing to connect to some giant server farm. And that means lower costs for AI services, better privacy for us, and a much smaller environmental footprint for the whole industry. It just opens the door for so many more people to innovate. But you know, maybe the most mind-blowing idea here comes from this quote from the researchers themselves. The fact that Wanda works so well without any follow-up tweaks, it suggests that hidden inside these giant, messy AI models, there might already be smaller, perfect, super efficient little brains just waiting to be uncovered.
And that leaves us with one last big question to think about. We started with this unbelievably complex billion-parameter problem, and we found an answer that was basically just simple multiplication. So, if a perfect, leaner version of a giant AI can be found with such an elegant little key, what other simple, powerful truths about intelligence itself are we missing, hiding right there in plain sight?